Hello everyone, and welcome back to our series on algorithms. In the previous video, we wrapped up our discussion of pure graph algorithms by talking about the all pairs shortest paths problem. In this video, we will look into algorithms concerning a special type of directed graph known as flow networks. If you enjoyed this lecture, be sure to like, comment, and subscribe. With that, let's begin. A flow network or capacitive network G is given by a four-tuple VCST, where V is a set of vertices, C is a capacity function which maps pairs of vertices to positive real numbers, and S and T are source and sink vertices respectively. Essentially, a flow network is like a connected directed graph, except each edge has an additional attribute called capacity. This capacity effectively describes how much flow is allowed through this edge. You can think of the edges as pipes, and the capacity as how much water they can carry, for example. Here's an example of how a typical flow network is depicted graphically. In this representation, we denote the capacity of each edge after the slash. You might be wondering why we didn't define a set of edges E when specifying the flow network G. This is because if the capacity is 0 for a given edge, we can essentially think of that edge as being non-existent. Hence, the capacity function is sufficient for encoding all the edges. Note that some definitions of flow networks will also include the edge set E, but these definitions are still equivalent. An ST flow is defined as a function f from pairs of vertices to reals which satisfy the following three properties. The first is skew symmetry, which means that swapping the direction of the edge simply negates the flow. Note that we can always assume that if the reverse of a given edge is not in the graph, we can, without loss of generality, add it and set its capacity to be 0. The second property is flow conservation, which means that for any vertex that is not S or T, all flow coming in must also all come out, meaning that the net flow is 0. And the third is the capacity constraint, which indicates that the flow over each edge should be less than or equal to the capacity of said edges. This is also sometimes referred to as the feasibility requirement of a flow. We define the value of a flow as simply being given by the total amount of flow exiting from the source. Next, we will introduce the notion of a ST cut. When we discuss Kruskal's and Prim's algorithms, we discussed the notion of a vertex cut in which a graph is partitioned into separate subsets of vertices. In this case, an ST cut is simply a partition of the graph into two subsets where one subset contains vertex S and the other contains vertex T. The total capacity and flow of a cut are consequently defined as the sum of the capacity and flow, respectively, of the edges crossing the cut. Now that we have introduced all these definitions, we might consider what kinds of problems we would want to solve concerning flow networks. Perhaps the most natural question to ponder would be how we can determine the maximum flow from S to T that's allowed in the given network. This brings us to one of the main theorems involving flow networks, the max flow min-cut theorem. The maximum min-cut theorem states that the maximum value of a flow possible in a given flow network G is equal to the minimum capacity of a ST cut. Intuitively, you can think of this as basically saying that we can allow as much flow as the most restrictive bottleneck in our network will allow. Before we can prove this theorem, we first need to introduce some more definitions. A residual network GF for a given network G and flow F is defined as a copy of G where the capacity function CF is instead given by CUV minus F of UV. An augmenting path is simply a path from S to T composed of edges with non-zero capacity in the residual graph GF given a network G and flow F. Lastly, the bottleneck capacity for a ST path is defined as the lowest residual capacity of an edge along this path given a network G and flow F. Now that we have defined these concepts, we can use the fact that a path can only be an augmenting path if and only if the bottleneck capacity is positive to restate the max flow min-cut theorem into the following three equivalent statements. First, there is an ST cut S where the capacity equals the value of the flow. Second, F is a max flow in G. And third, there is no augmenting path for F in G. Let's now prove the equivalence of these statements. First, we show that 1 implies 2. To do this, we must first assert a lemma which states that the flow of a given ST cut must be less than or equal to the capacity of the cut. This is trivially true since the value of a flow is given by the amount of flow crossing the cut, and this quantity cannot exceed the total capacity of edges crossing the cut, else the flow would not be feasible. Hence, we have that the flow of a given ST cut is bounded above by the total capacity of the cut. Therefore, if there is a ST cut where the capacity equals the flow, we have that the flow must be maximized, meaning that 1 implies 2. Next, we show that 2 implies 3. Suppose that f is a max flow in G, but there is also an augmenting path for f in G. If we add this augmenting path to f, we have a new flow f prime such that the value of f prime is greater than f, indicating that f is not a max flow. Hence, by contradiction, if f is a max flow in G, there must be no augmenting path for f in G. Lastly, we prove that 3 implies 1. If there's no augmenting path for f in G, we have that T is not reachable from S. Consequently, we can define a ST cut S where all vertices reachable from S are in S, while all other vertices are in complement SC. Since there is no augmenting path for f in G, we have that the residual capacity of all edges connecting the cuts must be 0. Hence, the total flow traveling across must be equal to the total capacity of the cut itself, thereby indicating that 3 implies 1. Therefore, we have shown the equivalence of these 3 statements, thereby proving the max flow min-cut theorem. Now that we have proven this theorem, how do we actually compute the max flow for a given network? Well, we have 2 main approaches which operate effectively the same. The first is the Ford-Fulkerson algorithm. Assume we are given a flow network G with integer capacity edges. Initialize the flow f equals 0. Using DFS, compute an augmenting path in the residual graph GF and augment the flow along the path by its bottleneck capacity. Repeat this process until no augmenting path remains. Here is a formal statement of this algorithm. The correctness of this algorithm trivially follows from the fact that if there is no augmenting path for a given flow, the flow must be maximal, as proven in the alternative formulation of the max flow min-cut theorem. Let us now calculate the worst case time complexity. Each DFS traversal is O of m time, where an edge in this case refers to a connection between vertices with non-zero capacity. Since the capacities are assumed to be integers, we have that each iteration will augment the total flow by at least 1. Hence, we have that we need O of f traversals, where f represents the value of the max flow itself. Hence, we have that the total complexity is O of m times f. Note that the complexity of this algorithm is dependent on the value of the maximum flow itself, meaning that even if the number of edges and vertices remains relatively small, if the max flow is large, the runtime will still increase substantially. Furthermore, realize that this algorithm only works with rational capacities, since any rational capacities can be scaled up to integer values, which are the only values for which this algorithm is guaranteed to terminate. Is there any way to get around these issues? Well, we could consider a second approach, the Edmonds-Karp algorithm. This algorithm is effectively identical to Ford-Fulkerson, except rather than using DFS to find augmenting paths, we instead use BFS to guarantee that we will find the shortest augmenting path. Since the algorithm is otherwise identical, correctness follows trivially. Looking at the complexity, we have that each run-through of BFS has complexity O of m. Since this saturates at least one edge of E, we have to perform O of m BFS runs in the worst case. Furthermore, since each BFS tree has a maximum size of n, we have that the overall complexity is O of nm squared. Hence, using this method, we can efficiently calculate max flow when f is omega of mn and when the capacities are any positive real numbers. Overall, Ford-Fulkerson and Edmonds-Karp are the 2 main approaches used to solve the max flow problem for flow networks, with the preferability of each approach largely being dependent on the types of capacities in our network and the size of the max flow relative to the number of edges and vertices. This ultimately concludes our discussion on graph algorithms, and from this point onwards, we will be delving into an eclectic collection of topics, starting with a brief dive into branch and bound algorithms. I hope you enjoyed this video, and I will see you next time.